When it comes to continuous functions on closed intervals, they are not like other functions. Unlike other functions, continuous functions exhibit a number of interesting properties when they are defined on closed intervals. In this lecture, we shall try to explore each one of these properties. The students are expected and advised to go through each property in a manner so that they are able to understand, comprehend, and master each one of them. For that, there are a number of functions that take positive isolated values. When I say there are functions that take isolated positive values, what I mean is that there may be functions that take positive value at a specific point, say C, but there's no neighborhood of that C, there's no surrounding of that C where the function is positive throughout. The similar is the case with negative values. However, when it comes to continuous functions exhibit this beautiful property. Whenever a continuous function takes a positive value somewhere in the interval, then we can always find out a neighborhood of that point. And throughout that neighborhood, the function will be not just continuous, the function will be positive. The same is true for a continuous function. There are functions that have ranges which are not bounded. For example, take the famous modulus function. The modulus function can be as large as we please, and it can be as small as we please. Similarly, there are functions like the greatest integer function, the range of which is an infinite set, and not just an infinite set but an unbounded set. However, when it comes to continuous functions on closed intervals, it can be taken for granted that the range of the function will be bounded. What it means is that we can always find out two specific values, say alpha and beta, such that there's no point in the interval where what we can infer from the previous property is that a continuous function defined on an interval is always bounded in as far as its range is concerned. Now, taking this one more step further, we can claim something more substantial than that. When it comes to a continuous function defined on a closed interval, not only will the range be bounded, but the function will definitely, inevitably take its maximum and minimum values in the interval. This is unlike the definition of a continuous function on an open interval. If you define a continuous function on an open interval and the function happens to be increasing, then the maximum and the minimum values of the function will not be attained in that interval. But when it comes to a continuous function defined on a closed interval, the function will not only have. Now, this one happens to be probably and arguably the most celebrated property of continuous functions defined on closed intervals. This is called the mean value property. All of you are aware about the function, the greatest integer function. We know that the greatest integer function takes the value 2 at a number of places. The same greatest integer function takes the value 3 at another number of points. However, there is no point in the domain of definition of the greatest integer function where the function will take the value 2.5. Now, this 2.5 is a value that is between 2 and 3. The function takes the value 2 somewhere, the function takes the value 3 somewhere, but the function does not take the value 2.5 anywhere. But when it comes to continuous functions on closed intervals, we already know that the function will attain its maximum and minimum values. Now, we can say something more than that. we can say that the function will not only have its maximum and minimum values, the function will not only attain its maximum and minimum values, but the function will take and attain and assume each one of the values that lies between its maximum and minimum values. This property tells us that functions like the sine function, when we define them on closed intervals like minus pi by 2 and plus pi by 2, we know that the least value of the function is minus 1 and the largest. This is the last but obviously not the least one. And this is just a redefinement of what we have learned already. The mean value property can be taken to infer something more about functions that take values of opposite signs at two different points. What I mean is that if there is a continuous function defined on a closed interval and there are 2 points in that interval such that the function is positive at one of these points and is negative at the other point, then obviously by the use of the mean value property, the function will take each one of the values between these two values. That is, the function will take every value between this positive value and this negative value. That tells us that in particular the function will be 0 somewhere. And this can be stated in a different fashion. Functions which are continuous and defined on intervals, if they become positive somewhere and negative somewhere, then those functions will definitely have at least one root between those 2 points where the function becomes positive and the function becomes negative. We know that